tape ahead. So just administrative-wise, I guess maybe it wasn't clear, but if you look at the website, hopefully that would have been clear. There are indeed going to be lectures next week. There's still some more material that I'd like to cover and make sure you guys get from coming out of the class. And perhaps actually more importantly, on the final lecture, which will be essentially a week from this Thursday, we'll do the Eta Kappa Nu review forms. So for once in the semester, I'll actually require you to show up in person, because otherwise I don't know how to get you to actually fill out that form. I'll post sort of more information about that on Piazza, but the main take-home message is indeed there will be lectures next week. Okay, so we were talking last time about offset cancellation, and we talked about sort of the first general category of both these correlated double sampling, and then we finished up with talking about this chopper stabilization or chopper type of amplifier design. So unless there's any questions on that, I want to move on and talk about the sort of second general category, which is essentially somehow figuring out how to inject a DC signal to cancel that offset. So before I do that, any questions? Or okay, good. So if we start thinking about this sort of second version or the second general technique, which again, the whole idea is just find some DC signal that will cancel the offset. I wanted to kind of remind you guys of one of the techniques that I believe you talked about in the multi-stage amplifier lecture, of actually how you would come up with that DC signal to use to cancel the offset in the first place. So let's say indeed you had some input, and this is where we're going to do the subtraction. And then we take our, for example, amplifier. And by the way, somebody had asked earlier, I'm drawing everything as real op amps here. The idea is very similar with OTAs, or in fact would basically work the same way. So if I wanted to figure out what would be the right signal to use to cancel that offset, then at least conceptually what I could basically do is take another amplifier, measure the output, and then just low-pass filter the output of that amplifier and use it to feed back. So the idea here being that if there is an offset, you'll see some big signal at DC at the output, or at some low frequency at the output of this original amplifier. So if I sense that there's that large signal and then feed it back, I should be able to get rid of that DC signal. And of course, the idea is that if this low-pass filter is really low-pass enough, then it would be getting rid of only these low-frequency content that I see at the output. Now, based upon the sort of confusion, or perhaps confused looks that I'm seeing, that's not to say that this only cancels the offset. So what else does it actually cancel if I do things this way? Yeah, it also cancels your signal. Now, which part of the signal does it cancel? Yeah, it cancels the low frequency part of the signal. So indeed, if I looked at sort of the transfer function of this amplifier, it would look something like this. Because indeed, at low frequency, that sort of extra amplifier that I added in, which let's just call it an auxiliary amplifier, again, whose only purpose in this case would be to measure the offset. Well, there's no difference between the signal and the offset at this point. So other than just maybe that, maybe your signal doesn't happen to have frequency components at DC, in which case, okay, this would just measure whatever's at DC and essentially cancel it out. Okay? So we'll fix this in 1 second. We'll make it so that the signal can actually get through at DC. But before we do that, is this really going to be sort of perfect in canceling the offset or not?
Why turn auxiliary amplifiers just to cancel like feed-forward connectors?
Oh, why did I have this extra amplifier here?
Yeah, you just right.
Oh, you're saying I could just take the output and feed it to a low-pass filter. Ah, okay. You could do that. The problem is actually very much related to the question that I asked. So if I just fed it into a low-pass filter like this, what's the sort of gain of the filter? 1, right? Okay, so that means that, by the way, you could indeed do that. It would just be a gain of 1. But as we had said with the input offset cancellation, the sort of net gain in this feedback loop I'm going to get will just be set by the gain of the amplifier in terms of canceling that offset. And so if your amplifier gain is high but not high enough, you won't necessarily track that offset out perfectly. Okay? Yes?
Sorry, it seems like if you're gaining up whatever you're capturing at the output, it's actually going to be even worse because you're potentially going to be canceling off like more signal than you actually have offset.
Okay, so the question was, if I really put a gain in this auxiliary amplifier here, is that ever going to do sort of, is it going to make it worse in the sense of canceling more offset than actually sits there? Well, let's assume this amplifier just has a gain associated with it. If that's the case, then this whole thing is just a feedback loop, right? And I can just write the output of that feedback loop as being A over 1 plus AF. Right? And so if I make that F very, very large, then that means the whole thing will just go to 0. Right? The whole expression there will just go to 0, which means I can never be canceling too much. Right? In other words, I can never have an extra offset going the other way. All I can do is make it purely go to 0. Okay, if you screw up the sign, then you're screwed, right? Because now you have positive feedback instead of negative feedback. That would certainly make things bad. Right? I meant as long as, of course, I don't screw up the signs of things, meaning I really have this as negative feedback. Okay, but again, let's assume this even has infinite gain. So this auxiliary amplifier here, let's assume it really does have infinite gain, at least at DC. Does this perfectly cancel the offset or not? There we go. This auxiliary amplifier might have an offset of its own. Okay? So you have to be careful of that because, of course, whatever that offset is, you're just really going to then attenuate it by the gain of this other amplifier in terms of its input referred effect. So if this thing either has a large offset of its own, or your gain of the forward amplifier is not sufficiently high, then you're still going to be limited by whatever that auxiliary amplifier offset actually is. Now, just because we're going to come back and sort of look at this again a little bit later, I'll just point out that there are indeed ways of getting rid of making it so that I can still actually measure the DC of my input signal. So as you might imagine, the way we're going to do that is by adding in some switches here and there. Okay, so I won't draw it for now just because, again, we're going to come back to it a little bit later on, and we'll see sort of how we really do that, and why it will actually maybe drive us to a slightly different way of implementing this exact kind of idea. So just keep that in the back of your head for now. So the first thing I wanted to mention is just how would we actually build this so-called auxiliary amplifier. And so if you paid attention, what we really needed to do was something that essentially added or subtracted in a signal from the input and then fed it into our amplifier. So it turns out there's actually a somewhat more convenient way of building this, which you can kind of derive by shuffling around the block diagram a little bit. Okay? So I claim that this sort of picture here is functionally identical to doing the following. Okay, so let's just say this is my V off or my V cancel or whatever. That's V off. That's V in. That's, of course, V out. Okay, all I did was rearrange the order of multiplication and addition. So now, can anybody tell me a really convenient way of building the equivalent block diagram on the right? There we go. If you use OTAs, you just sum the currents and then actually dump them onto the same node, and it'll get converted to a voltage. Okay, so let's actually just draw that block diagram quickly. So if this is my V in, I'll just draw this literally as a node now. This is my other OTA coming from a V offset. And then there's some fixed or common load resistance here. And then indeed, that's how I would sort of implement something like this. Okay, so just to be absolutely 100% clear, if I was to do this with a simple resistively loaded amplifier, that would imply the whole thing would look something like this. So I'd have my V in plus, my V in minus, then I'd have a second input differential pair, or rather a second differential pair, that would then be connected to something like V off plus and V off minus. Now hopefully, just to be sort of sure that everyone is clear on this, if I wanted to do a subtraction versus an addition, then because it's differential, you just flip which side is tied to plus and which side is tied to minus. Okay, so that's one nice thing about differential circuits, is that it's very easy to do, it's just as easy to do subtraction as it is to do addition. Whereas with single-ended circuits, you have to sort of, you can't exactly quite do it this way. You have to have current flowing one way or the other to do an addition or a subtraction. Make sense to everybody? Okay. So, before we move on, there is one thing that I sort of had skipped from some previous things that I wanted to mention in this context. So, let's go back to this earlier picture here. Right? So, if I really wanted to build something like this, let's assume that the signal maybe doesn't have any content at DC, but at some pretty darn low frequency, it does actually have stuff that we want to make it through. That implies that what we really want to do is make this low-pass filter kind of have as narrow as a bandwidth as we possibly can. In other words, we want to make it have very, very low pass. Now, if you think about it, the sort of simplest way you might build that would be, for example, with just an RC filter. And if you want it to be very, very low pass, meaning to have a very, very low frequency response, you'd need a very large resistor. And then, unfortunately, the resistor A will just physically be big, meaning take a lot of chip area. But B, you're also then going to be sort of sensitive to all the variation mechanisms we had talked about. So it turns out that particularly in those contexts where you want a very, very low frequency filter, there's kind of a clever way of building a resistor that actually gets around both the physical size of the filter and actually allows you to control the sort of low pass filter time constant very, very precisely. So to show you how something like that might work, we have to do a little bit of a thought exercise that at first maybe screws with people's head a little bit. So just bear with me for 1 second. So let's say that indeed I wanted to build the equivalent of a resistor. Well, let's just first think a little bit carefully about what we really mean by having a resistor. So let's say we have a V1 and a V2 here. And hopefully that will go away. Okay. So with a V1 and a V2, basically meaning we're applying a voltage of V1 minus V2 across this resistor. Then hopefully you all are very clear that the current is just V1 minus V2 over R. Right? That's just by definition. Well, what I'm going to do in 1 second is try and build a circuit that, rather than sort of flowing this current continuously in time, moves that current in kind of packets of charge. Okay? So if I'm going to move it in packets of charge, then I can also say that the charge I get in some unit time is just that current, which is of course V1 minus V2 over R, times some delta t. I've done nothing except, just sort of multiply the current by delta t to figure out how much charge I moved in that unit time. All right, so keep this in mind, because now I claim that I can actually build a resistor out of some switches and a capacitor. So I'm again going to apply V1 and V2. I'm going to take a clock signal. I'm going to have the clock turn on that switch in the first phase and turn on that switch in the second phase. So in other words, in the first phase, I just connect the capacitor to V1. And then the second phase, I connect the capacitor to V2. So now, you guys tell me, over one clock cycle, how much charge gets moved from V1 to V2? And let me just label this capacitor as being C. So by the way, in the first phase, when you connect the capacitor to V1, how much charge will end up on that cap? Yeah, CV1. Okay, when you then connect the capacitor to V2, how much charge ends up on the cap? Okay, so now how much charge did you transfer from V1 to V2? Yeah, so it's just going to be C, V1 minus V2 is the amount of charge you transferred in one cycle. All right, well now hopefully you're seeing where I'm going with this. Because if I want to equate this switch capacitor to a resistor, then all I'd have to do is equate the amount of charge I moved with a switch cap circuit to the same amount of charge I would have moved with an actual physical resistor. So in other words, if I want to know what the resistance of this switch cap thing is, it's just going to be, and I'm just going to sort of do this by sort of, manipulating the equations a little bit. So it's essentially going to be, and I'll just write this in a slightly different way. So R here is just equal to V1 minus V2 times delta T over Q. Okay, so if I just follow that same thing, V1 minus V2 times whatever the clock period is, divided by, as we said a second ago, the charge is just C times V1 minus V2. So in other words, the resistance of my switch capacitor circuit here is just 1 over C times the clock frequency. Let me just call that F clock. Okay, and the only sort of step I did there was obviously eliminated V1 minus V2 from top and bottom and flipped T clock from being on the top to being frequency on the bottom. So by the way, keep this sort of thing in mind because this pops up all over the place. Actually, not just in sort of analog circuits like this, but actually even in the sort of, when you took 141, when you said that the current was CVF, well, guess what? The resistance from CVF is just 1 over CF, exactly like we did here. Now, why did I bother doing this? As I said a second ago, I wanted to use this kind of circuit to generate a low-pass filter that would A, be compact, and B, have very well precisely controlled time constant. Well, the way I'm going to do that is I'm going to take this same switch cap resistor and just use it as the resistor inside of my RC low-pass filter. So let's call this C1 and C2. Again, this is clock and clock bar. Okay, this is, for example, my input. This is my output. All right, so as we said a second ago, the resistance is just equal to 1 over C1 times the clock frequency. And just like with any RC low-pass filter, I could say that the time constant is just R times C. Well, if I then use that, meaning I use the actual value of the resistance, then it tells me my time constant is 1 over C1 times the clock frequency times C2. Well, notice that basically says the, let's say, cutoff frequency, or the bandwidth of that low-pass filter is, of course, just 1 over the time constant, which tells us it's just the clock frequency times times C1 over C2. And notice, this first thing here is, of course, just set by matching. In other words, as long as C1 and C2 are built out of the same thing with the same unit cells and etc., you can make that ratio very precise. And hey, this clock frequency, if I have a chip that's running at a certain clock or a certain speed or whatever it is, I probably have that clock frequency anyways, and it's probably locked to some mechanical crystal or other very precise element. In other words, notice by doing this, I could indeed build a low-pass filter that first was very precisely referenced against a known sort of clock frequency. And second, if I want to make it to be very, very low pass, well, all I have to do is make C1 a heck of a lot smaller than C2. Whereas before, I had to build a really, really big resistor. Right? Physically big, I mean. Make sense to everybody? Or? Yes?
I mean, is it still something equal to make C1 much, much smaller than C2? Like, at some point, things are going to have to be really big, unless, because I feel like if we make a really tiny capacitor, it might be hard to get it to be as precise as you want.
Okay. So the question was, well, hey, at some point, aren't I going to be limited by sort of how small I can make C1 relative to C2? And indeed, that is possible. Now, notice, nobody said I had to use my original clock frequency for this thing. I could actually use something that's running even slower than that. The only thing you have to be careful of is, notice this is indeed a sampled circuit. So if I just take some signal at the input here that can have any arbitrary sort of frequency content going into it, then I have to make sure that this clock is running fast enough that I don't alias that input. But as long as I make sure that the bandwidth going into this thing is relatively small compared to my clock switching frequency, I can always just drop that clock switching frequency to drop the equivalent time constant, to increase the equivalent time constant of the low-pass filter. But you're of course right, eventually you're limited by just how small you can make the C1 versus the C2, although even there's tricks you can play where, for example, you stack unit cells on top of each other, as opposed to putting them in parallel, that even then you can probably push this to be exceedingly low frequency. It's a very good question, though. Any other questions on this? Or? Okay. So now let's sort of come back to our main point. And to do that, I'm going to sort of come back and figure out how is it that we could take this auxiliary amplifier idea and make it so that we could still actually get quote-unquote DC signals. In other words, let's say that our input signal really did have stuff at very low frequencies that we cared about. How can we use the same idea and make that happen? So the simplest way to do it is basically to say, well, you know what? If my offset is really sort of a DC or static thing, then what I'm going to do is that at startup, I'm going to configure my amplifier into something that looks like sort of a lot like that negative feedback loop we had applied before. But since I really, really want to make sure I completely canceled the offset, I'm going to take the output as an example, feed it in an OTA, and then a capacitor before I feed it back over here. So by the way, all I'm trying to build with this OTA and capacitor combination is an integrator. Right? Because if I have an integrator, then I'm saying at DC I have infinite gain. So I'll completely kill whatever the offset of that structure actually is. So now once I've done that, during normal operation, I take the input signal, I have that connected to my amplifier, and I basically just disconnect the OTA. In other words, I store whatever signal I calculated I needed to store, or rather, whatever signal ended up being accumulated onto that capacitor. Once I'm really operational, I just leave it there on the capacitor. And from all time forward, I'll just always be sort of canceling, or rather subtracting that signal out. But I can still recover these DC signals at the input. Make sense to everybody? Or? In other words, I just sort of selectively ran this feedback loop once to measure the offset, and then I'm just going to leave it there for all time moving forward. Now, conceptually this is really nice, but there's unfortunately a quote-unquote minor problem. So what's the minor problem here? Sorry, say that again? Okay. So you said you're eventually going to lose the charge you sampled on your capacitor. Is that what you said? Or yeah, that's absolutely right. Now, by the way, where do you lose that charge? What's the most likely culprit for that charge leaking away somewhere? Through the switch, right? Unless you have a zero leakage switch, which, okay, there are some crazy people, including me, who tried to build those kind of things, but don't worry about that. That's not reality just yet. Unless you have a zero leakage switch, sorry, there's always going to be some current flowing through there. And eventually, the voltage on that capacitor will not be what it was supposed to be. It'll leak off to something else. Okay, that kind of sucks. So I claim that there is actually a way we can do this. We just have to sort of, let's say, break from from the normal, let's say, mode of operation that we're using here. Okay? So in other words, what I would like to do is actually build something that will store a value for as long as the power supply is there. Anyone know of a good way of doing that? Yeah, a digital circuit. Okay, so what kind of digital circuit in particular do you need?
Register and
Yeah, okay, so I need some kind of register, right, to store whatever the digital value is for some period of time. And as you said, I also probably need a DAC to convert whatever the value of that register is into an actual voltage. Okay, so let's actually draw that picture. So same basic idea. I'm going to take my input signal, or more generically something that could be forced to ground so I can do the sort of offset cancellation. And by the way, this is the sort of trimming idea where we're really only doing this once at the beginning of operation. And so now, as we said a second ago, rather than having some capacitor, I'm going to have a DAC. The output of that DAC will be fed by, let me just call it an accumulator, but really that's just a pile of registers and some additional logic that I'll explain in one more second. This will be my output. And so now the only thing we have to do is add one more element to kind of close this feedback loop. So what's the other element that I need? Yeah, I need an ADC. I have to look at that analog output over there and convert it into a digital value so that I can then use that digital value to correct the offset. Now, by the way, I labeled this thing here as an accumulator because remember what I'm trying to mimic is an integrator. So in the digital domain, an integration is just an accumulation over time. Same exact idea. Make sense to everybody, or? Yeah. No, so the idea here is that you would do this just once at the beginning. In other words, you would you'd basically replace this OTA plus capacitor with this ADC accumulator and DAC. You'd run it once at the beginning, and then when you're done, you basically turn off this ADC, meaning you essentially feed zero quote-unquote input to the accumulator, meaning you don't change that accumulator code anymore. You just have that drive the DAC, and then as long as the power supply is up and there isn't some weird random noise particles or whatever it is, the DAC will just keep its value constant.
Sorry, just to clarify, so the VIN initially is actually ground.
That's right. Initially, the VIN would be ground, just like it is right here, right? Because our purpose there is actually to get rid of the offset, not to get rid of the initial value of VIN. All right, so now a couple of questions for you guys. And let me start with the first one first. So the first question is, how much resolution do I need in this DAC? In other words, how precisely do I have to be able to set the voltages at the output of that DAC? I don't need a number, by the way. I want sort of conceptually.
The LSB has to be around your noise.
Okay. You said it has to be around your noise. So that's maybe one way of saying it, although that it doesn't necessarily have to be the same as the noise. But what's another way of, let's say, phrasing that? Yeah, exactly. So the resolution of that DAC is really just set by what's the smallest offset you want to tolerate. Okay? So in other words, you want that the LSB or the step size is set by whatever your offset budget is. Because as we'll see in 1 second, or as perhaps should be obvious, if that DAC has finite resolution, you can never perfectly cancel the offset, right? You can always only get to within sort of basically a step or maybe half of a step if you're lucky and things happen to be balanced just the right way. And again, we'll see that in more detail in 1 second. Okay, so that tells us how big the step needs to be, but how many of those steps do you actually need? Yeah, exactly. You need to be able to cover whatever the full range of offset is. So as an example, let's just say you wanted 99 or whatever percentage yield 3 sigma translates into. This 3 sigma offset would set the sort of total range of your DAC. So as an example, if you knew that there was going to be up to 100 millivolts of offset, and you wanted 1 millivolt of residual offset error, that basically means you need, roughly speaking, 7 bits of resolution. Or in other words, approximately 100 and something steps in your DAC. Is this clear to everybody? Or? All right, so now here's actually a much more interesting question. How many bits of resolution do you need in that ADC? So let's go back to the earlier example. Let's say that indeed I had the 7 bits of range I needed in my DAC. Who thinks you also need 7 bits of dynamic range in the ADC? Okay, who thinks you need less than that? Okay, good. How many do you need precisely?
1.5.
No, it's actually 1. Okay, we'll see how it is. So, by the way, what is 1 bit of resolution? What kind of circuit is that? Or 1 bit ADC, excuse me. It's a comparator, right? All right, so now let's see why it is you can actually get away with just 1 bit of resolution. And by the way, of course, this works most nicely when you're actually trying to cancel the offset of a comparator in the first place. Because, hey, you have a comparator already, so now we don't have to rebuild another comparator. Okay, now you can actually take the ADC and replace it with a comparator. I'm just going to draw the picture here as if we're trying to cancel the offset of a comparator in the first place. So let's say we have our comparator. And by the way, I'm going to draw everything single-ended, but we'll see how to do this with a differential circuit in 1 second. So this is, again, our input, where, as we said, when you're doing the offset calibration, the input will just be forced to be 0. We'll have our DAC. We'll have our accumulator. And now, since we have a digital output coming out from the comparator anyways. We're just going to take it and directly feed it into the accumulator. So now, why does this still actually work? Well, let's just sort of watch what would happen in time as we ran this initial feedback loop. And so initially, let's assume that as an example, and let me just label this thing here. Let me call that V off. So this is time. This is going to be, as an example, both V off and the digital output from the comparator. Let's assume that initially the offset voltage was too low, meaning that the output of the comparator is going to be a high. All right, well, in the first clock cycle, if I have a high coming out of the comparator, the accumulator will say, okay, I need to step up, right? It'll step up the output voltage. If I repeat it and it's again high, again, it'll step up, right? And so actually, as long as this output is high, the thing is just going to keep stepping that voltage up. And I'm just going to stop there just so that it's easier to draw. Well, now, let's assume the actual offset is sitting, let's say, right here. So that's where the real sort of offset of the comparator is. Well, once the output of the DAC gets above that offset, the next time we evaluate it, the comparator output will go low. Well, guess what? Once that happens, the accumulator will get updated, and its output will drop down by 1. Well, okay, and then next clock cycle, output of the comparator goes high, accumulator jumps up by 1. Next cycle, output of the comparator goes low, accumulator jumps down by 1. And so on and so forth. Okay, so notice, even though each time my comparator was just telling you, do you need to go up or to go down? As long as the steps happening at the output of that accumulator, meaning the steps in the DAC, were basically small enough, then basically what's going to happen is that once I get near that offset, I'm just going to sit there and do what's called dithering around that code. Or in other words, around that value. Because each time the comparator will just say, well, go up, go down, go up, go down, go up, go down. And I'll be sitting right along where I wanted to actually be. So in other words, the real trick here is that because I'm really looking for an average quantity in the first place, I don't really need a super high resolution estimate of that quantity to begin with. Right? I can just say, look, am I farther away or closer to where or rather, am I above or below where I want to be? And then as long as I take really, really small steps in the direction I'm trying to go, eventually I'll sit and dither right around the actual value I wanted. Yes?
When do you know when to stop?
When do you know when to stop? Okay, very good question. So there's a few sort of simple answers. So in this kind of scheme, what's the maximum number of clock cycles you'd have to run this thing to converge? Yeah, so if I have n bits of resolution in this accumulator, I know in the absolute worst case, I can only take 2 to the n steps before I'll have covered the entire space, right? And I'm guaranteed to converge. So that's one easy way of doing it. A slightly more sophisticated way would be to look at the output of this thing and see whether or not it's really changing, more than one code over time. Right? So if I suddenly start seeing this dithering pattern, I can say, okay, fine. Once I see that, I'm going to stop. Now, you do have one interesting point or perhaps question that you may have been asking, which I'll turn around on you guys. So let's say indeed I either run it for some fixed period of time or I look for this 1010 kind of sequence and then I just stop. How big is the worst case residual offset going to be? Let's not worry about noise. Let's assume this is all perfect. So I just have this DAC and a perfect comparator. It's a full 1 LSB. It's not half, right? Because you could just get unlucky, right? In other words, you could get unlucky, and this offset level here happens to be either right next to the code above you or right next to the code below you. And because you just so happen to stop on the wrong clock cycle, you picked the code that was a full LSB away. Okay? So in general, with these kind of systems, you have to design it so that that 1 LSB is the full sort of residual offset that you might be willing to tolerate. No extra factor of 2. Make sense to everybody? Or? Okay, great. There's actually a couple of other ways you can kind of interpret this in terms of, essentially as you're running this thing, what you're really doing is adjusting the threshold of that comparator. So let me just quickly draw that, because sometimes it does help people to understand the general concept. So remember with a comparator, what we're basically looking at is a V out versus V in curve that, as an example, let's say I had an initial offset, would look something like this. So what I'm really doing with this loop is every time I notice that my comparator says that there's either a 1 or a 0 coming out, that's basically telling me, well, which direction is the offset actually sitting in, the residual offset. So as an example, if I have my comparator tell me that there's an output of a 1, which would have been the situation with this particular thing if I put a 0 input, it says, well, okay, my offset must be too big. Let me move to the left. So then this would, for example, be my new curve. Right? Then again, it says, well, offset's too big. Let me move to the left. And then, oh, okay, if I do it one more time, now I've actually crossed the threshold. Now if I repeat this one more time, it'll say, oh, actually, sorry, your offset is negative. And then it would push you back to that other curve there. And as you can imagine, you'll just start looping on those 2 points. Yes?
If we were to implement this with just like a regular amplifier and some comparators, so if you had like amplifier and another comparator, so basically like a grouping picture.
Uh-huh.
How do you know where to set the offset of that second comparator?
Ah. Okay, great. So to maybe just quickly rephrase your question, what you're basically saying is, hey, look, this ADC, which maybe really is just a comparator, may itself also have offset in it. Right? In other words, if this thing has an offset in it, then just like we had said with the earlier picture, if there's any offset here, this output would converge to that offset and not necessarily to 0 differential output. Was this your question, by the way? Or? No? Okay, so what was your question?
I think it was if you're setting up so you're just setting it up assuming like a 0 threshold. Understood?
Well, why would I want anything other than a 0 threshold on this? Like ideally what I want is a 0 threshold there, right? Oh, are you asking about, for example, in the 4PAM case? Or?
Yeah.
Oh, okay, I see. So everything I've drawn here is assuming that what I really wanted to find was the 0 point. Okay? Let's say I wanted to find a different point. Let's say I wanted to find, for example, some, 300 millivolts. You guys tell me, how would you do that? Yeah, you just set V in to be 300 millivolts and you run this exact same loop. Right? Because the comparator doesn't really care. It just says, are you above or below whatever the input actually is? Okay, so indeed, if you wanted to offset, quote unquote, cancel at a different threshold, you just apply that threshold at the input, you run this whole loop, and guess what? You'll find exactly that point. By the way, that brings up actually another interesting issue or an interesting point, which is that when I really build this DAC, I actually don't even really care about much of anything in that DAC, except what the smallest steps you actually make are. Because notice, at the end of the day, what's going to happen is just that I'm going to be sitting there and kind of dithering around one code. Now, you do have to be a little bit careful. If you have a DAC that, for example, has a curve that looks like that, that's bad. Okay, that would actually cause you some additional problems. Because then, in the worst case, you might get stuck around this, or you might actually dither over a whole bunch of codes. But as long as your DAC basically is guaranteed to always move in one direction, then because you have this feedback loop here, any sort of nonlinearity or badness in that DAC, you can think of it as just being thrown away by the feedback loop. In other words, it's really forcing you to sit on one particular spot in that curve. And then all you care about is exactly how big those residual steps are, because that's really what sets your remaining offset in the whole system. Now, maybe just to sort of quickly address one other thing, you could have been asking the question of, well, what happens if this ADC has offset? Or rather, more generally, let's say I use a comparator for this feedback thing, and I really want to zero out the offset of this amplifier. Meaning, I really want everything to go to 0, like, in terms of the remaining offset. Well, you guys tell me, is there a trick I can play, now that you know this, to actually make this whole thing go to 0 offset? Yeah, exactly. So we just convinced ourselves that we can offset cancel the comparator, which is our ADC. So you'd first offset cancel the comparator itself. Then you use that offset canceled comparator to cancel the offset of whatever thing it is you're trying to measure in the first place. Okay? So these ideas are actually quite powerful in that you can really apply them more generally to many multiple stages of amplifiers, multiple stages of comparators, and so on and so forth. Because as long as you know how to cancel one of them, you can kind of bootstrap, right? You can use that good known thing to cancel the others and then repeat the same procedure. Make sense to everybody here? All right, so now let's talk a little bit about how we're actually going to do this. In other words, how we're actually going to build these DACs that we're talking about, or rather, really, how we're going to build something that's going to take the offsets of our, in this case, comparator, and really modify it in some way. So, turns out that there are, for all intents and purposes, an infinite number of different ways to introduce a digitally controlled offset into a comparator. And for better or for worse, I think people have tried probably just about all of them. So if you go and you look in the literature, you'll see like a bazillion different circuits that all will claim to cancel an offset. Having said that, you have to be careful in terms of how you really pick what you're doing. And in particular, there's a few really key issues. The first is that depending upon how you do it, your offset cancellation circuit may actually cost you some extra power. And if you think about that, that's kind of annoying, right? Because remember we always said that power should only be spent to like drive transient signals? Well, you may actually have to spend some power to cancel this offset. Another very important issue is that we're typically talking about differential circuits here. And remember, the whole reason we went to a differential circuit in the first place was we wanted to reject things like power supply noise, common mode noise, and so on and so forth. Well, unfortunately, in order to cancel an offset, you almost always have to intentionally inject some asymmetry into the circuit. Because offset really means there was an asymmetry, and so the only way for you to get rid of it is to create another asymmetry. So just to give you another, an example of one way of doing that, which would be kind of a bad way, as an example, let's say that you canceled the offset by taking your originally symmetric, nice differential amplifier, and then instead of having 2 kilo ohms on both sides, you have one side be 1 kilo ohm and the other side be 2 kilo ohm. Trust me, you can indeed cancel offset this way. It will quote unquote work, but probably will have really crappy power supply rejection, really crappy common mode rejection, and so on and so forth. So this circuit imbalance is really sort of a very important thing to keep in mind in terms of, okay, I want to cancel an offset, but how do I do it in a way that will minimize the additional asymmetry I introduce into the circuit in the first place? All right, as we spend some time discussing, you're of course going to care about the effective resolution, meaning how big your steps actually are in terms of changing a digital code somewhere, and how that translates into, let's say, X millivolts of offset. And finally, although you maybe will not care about this too much in this particular project, this is actually an issue that can come up quite often. Obviously, whatever you do will have some extra area associated with it. And so in particular, if you need a lot of bits of resolution to cancel that offset, that tends to imply the DAC you need to build will be pretty large. Okay, so just keep that in mind because that is an issue that will come up. So, having said all that, what I'd like to do now is walk through a couple of possible sort of implementations for how we would really do this sort of comparator trimming or offset cancellation. So the first one I want to briefly mention, only because it's kind of an interesting reminder about how the strong-arm comparator actually works, is we're actually going to do a DC offset cancellation by adding in capacitors. Okay, so to see how that works, let me just draw sort of the basic part of the strong-arm. Okay, so that's my strong arm. Of course, I've got some pre-charge devices up over here. And so one of the, let's say, maybe not most famous, but one of the, let's say, famous ways of canceling the offset of this particular comparator is actually to add intentionally variable capacitors onto the two sides right there. So now you guys tell me, how in the world does adding capacitors onto this comparator allow you to cancel the DC offset?
Well, you're going to adjust the slope of like the amplify stage with the
Yeah, exactly. So if you guys remember, initially, if we looked at those output waveforms, we had both of them, let's say, starting at VDD. And the whole goal was to make it so that one of them went down faster than the other one did. Well, of course, those slopes are just related to I over C. So if I change the capacitance on one side versus the other side, then that means that even with the same input voltage, the slope will be different. That would therefore mean that if you wanted to actually make the slopes be the same, meaning you have zero offset, that means you have to apply a different input voltage into the comparator. Make sense to everybody? Or? So, indeed, this works. But again, unfortunately, maybe is not, let's say, the most efficient way of doing things. So, by the way, just to maybe, since we haven't mentioned it before, the way you might actually build one of these variable capacitors, let's say in the simplest example, which would be something like this. You'd basically take an array of these unit elements, which would maybe be scaled relative to each other. So for example, 1x, 2x, 4x, and so on and so forth. And you'd basically tie them to some digital switches. So let's say D0, D1, D2, and etc. So by doing this, and then of course this is the node I'd actually connect on that side over there. By doing this, by turning these switches on or off, I'm basically programming how much or how many of those capacitors really show up and load the output. So let's go back to our sort of earlier example. Let's say that you wanted 1 millivolt of residual offset resolution, and you also had 100 millivolts sort of 3 sigma range you needed to cover. What might be painful about doing the offset cancellation this way? Okay, you said it's a lot of caps. Why is that bad? Ah, okay. You said they'll never be completely off, right? So remember, these transistors, they've always got some parasitic capacitance associated with them. So even if you turn the transistor off, there's still going to be some effective capacitance looking through that node there. So now, why is it particularly bad in this example that I gave where I wanted, this 100 millivolt range with 1 millivolt resolution? How many of these sort of total, if I count the number of unit cells here, how many capacitor unit cells do I need? Say that again? 2 to the 7. Okay, I need about 100 of them, right? Well, if each one of those capacitor unit cells has some, let's say, I don't know, a femtofarad of parasitic cap that you just can't get rid of. Well, guess what? What you just did is you threw 100 femtofarads of cap on the output of this comparator here. Which, if you guys remember, I said that you generally want to make those comparators small, right? Like minimum size. Well, 100 femtofarads is probably way bigger than anything remotely related to what you actually wanted in your comparator. Okay, so in other words, the badness here is that essentially you have to take that full dynamic range in the DAC and put it right at the most sensitive node of your comparator. And so if there's any sort of small parasitic that you can't get rid of, it will scale with the resolution of your DAC. And it will directly eat into essentially the power you have to spend to actually get this thing to work. Make sense to everybody? Or? Yes?
Sorry, you're saying that you have, oh, wait, you're right.
Okay, no problem. The other thing I'll mention here is that by adjusting the capacitors like this, we said that our simple model here showed that this, was saying that the slopes of the waveforms there was just proportional to the inverse of the capacitance. Well, turns out I lied a little bit. Okay, and the reason I lied is that unfortunately these input devices here, they're not really perfect transconductance in the entire sort of region of operation. Right? Because these two nodes right here, they're both tanking towards ground. And unfortunately, as you change the drain to source voltage, that will actually change the GM of the devices as well. So it turns out that this offset cancellation trick here is not really super linear with the code that you apply. The reason that that's bad is that even though we may not care on the net about linearity, if you kind of think about it, if I fix, let's say, the two endpoints, meaning that I say that, this is what I'm supposed to be applying in terms of offset versus code on one end, and this is what I want to apply on the other end. If I fix those 2 points, and then what I'm interested in is the largest, or rather the largest step size you get in between, well, the way to minimize that step size is to make this line perfectly straight. Because if, for example, the line actually does something like this, or equivalently something like this, well, notice what that basically tells you is in this case, those initial steps are bigger. And similarly, in this case, the later steps are bigger. Okay, so in general, even though we don't really care that much about linearity, it's still a good idea to try and make this sort of transfer between input offset and the code relatively linear, just because it really allows you to get the sort of smallest steps for the same number of unit elements inside of this DAC, however you actually build it. Is this clear to everybody, or? Yes?
So a couple things. First, wouldn't we want to actually operate in the top curve regime because the step size will be smallest?
So you said, wouldn't we want to actually operate in this region right here if I had this kind of curve? So yes, absolutely. The only problem is your range is more restricted. So that's why I said that if you always fix the range you're covering, the best way to make the step sizes small is to make it a linear map. Because if you always fix that range, it should be pretty clear that anything that's not perfectly straight has, a region where the slope has to be higher than it would have been if it was straight. That's really all I'm saying. Second question, or that covered it?
So why isn't this capacitance control done with MOSFETs whose value is determined by that voltage difference?
By which voltage difference?
Where you see, like in the cycle, where the curves kind of spread out, it's kind of a feedback mechanism.
I see. So the question was, why don't you sort of do this by MOS capacitors whose value actually changes with this differential voltage? There's probably something similar like that you could do, where you'd, for example, tie the capacitors in a bridge across here. But at the end of the day, it's still the same basic idea in that you either want that capacitor to have an effect on the output or not. And any which way you do that, there's always going to be some extra parasitic capacitance that you can't get rid of that will basically load the output of this comparator here. That's really the fundamental issue. Okay. So, just for the sake of it, can anybody think of another way of canceling the offset of this kind of comparator? Some other sort of thing you can inject or add to try and change the offsets? Yeah. Yeah, there we go. So, you could just pull some current out of one side or the other. Okay, now I drew it at those two input nodes there just because partially I was lazy. You could do it at the output as well. But what you're basically saying is, well, okay, indeed. Here I was using the cap to try and change those slopes. Here I can actually just try and do it by changing the currents. And by the way, again, just to be sort of totally clear, the way you might build something like that, just as an example, would be you take a bias voltage, and then you either feed that bias voltage to the gate of a transistor that you're going to use as a current source, or you ground the gate. And then you take a bunch of these guys and connect them in parallel, meaning you tie the drains of all those current sources together. Okay, and that, of course, would be your output current. Okay, so indeed this works, but much like with the previous example, unfortunately, if we needed, for example, a 7-bit controllability there, again, we'd have 128 of these unit current sources. And if each one of them had even, let's say, a femtofarad or half a femtofarad or some other pretty small capacitance, well, once again, we're directly loading the outputs of our comparator with that capacitance. Bad news. Okay? Causes us to spend a bunch of extra power. Yes?
Can you change the pre-charge circuitry?
Change the pre-charge circuitry. So what do you mean by that?
So that they don't start at the same voltage with us.
Okay, that's an interesting idea. So you said, could you change the pre-charge circuitry so they don't start at the same voltage, but rather actually start at a different voltage? you could indeed do something like that. The trick you have to be careful of is now that you have to basically build the voltage DAC that creates the different voltage for those two things to actually pre-charge to. But that's a valid thing to do. So you said it won't load the rest of your circuitry. It actually depends how you build the voltage DAC. But you're right, there is a way you can do it that would not have it load. Okay, great. So you said can't you just sum them all and combine them into one device? That is actually true, but we have to think carefully about how that might help. And so, by the way, to do that, let me sort of show you what I think is actually the typically easiest or best way to do this thing, and we'll get to exactly the sort of the point that you're making. So if you guys remember, we argued a while back that you were probably going to have to use a preamp in your comparator simply due to kickback, right? Simply from an isolation standpoint. Well, I would actually argue that once you've got that preamp, your best bet is actually most likely to do the offset cancellation inside of the preamp. And there's several different reasons for that. But let me draw sort of how that might look, and then I can explain why I say that. So let's say this was my original preamp. So Vin plus and Vin minus here. And much like we had done with the strong arm a second ago, what I'm going to do is just add in some extra current in order to create an offset. Now, just for the sake of simplicity, although you can do something more sophisticated than this, I'm going to assume that I'm really just going to dump that current onto one side or the other. In other words, once I know what the sign of the offset is, I will either turn on this transistor or that transistor. Right? And that, by doing that, that just decides which direction I'm applying the offset. Okay, and as with before, that current source over there, so let's call this I bias, and this will be I off. This will now be sort of my current DAC. All right, so as Paul was mentioning, one thing that's immediately nice about this is that, yeah, I have to build this sort of DAC here that has a lot of bits or many, let's say, unit cells inside of it. But if I keep this transistor here in saturation, meaning whichever one of these two is actually on, it kind of acts like a buffer, right? It kind of acts like an isolation. Because remember, we said that there's always a GMRO relationship between sort of voltage swing happening here versus voltage swing happening there. That's true even dynamically, meaning that even if there's a big cap sitting right here, as long as the RO of this device is pretty high, you don't really care that there's a big cap sitting here, right? It doesn't really load your high-speed output. Okay, so this is actually a really, really nice trick to make it so that you can push that DC offset cancellation thing, even though it's going to have extra capacitance and parasitics and etc., to not really significantly load your high-speed signal path from a capacitance standpoint. You are loading it with an RO, but now this is another reason why this is actually a very nice way of doing things. So remember, what did we say we wanted the preamp, how did we say we wanted to design the preamp in terms of this RL relative to the RO of the input devices? Yeah, we wanted the RL to be very small. Because if it wasn't small, we were going to be more sensitive to the common mode kickback from the comparator itself. Well, just like these devices, if we make the RO of these sort of offset cancellation devices high in comparison to these load resistors, well, first of all, from a, let's say, DC gain standpoint, it won't load you too heavily. But more importantly, from an asymmetry standpoint, right, if these ROs are all big, and your impedance is really dominated by that load resistance in the first place, well, circuit still looks pretty darn symmetric, right, at least from an impedance standpoint. So I'd actually argue that's another sort of nice benefit of doing it this way, which is if you really make the output impedance of the sort of input devices and of that offset cancellation device high, then actually you don't have to load it in terms of capacitance parasitics. You don't have to basically screw up the symmetry. Both of those are really, really nice, which is why this is kind of my default solution. Now, having said that, there are a couple of things that are not so great about this. So what's the first thing that's maybe not so great about this? Yeah, I have to spend power, right? Notice I've got DC current flowing here, whose only job is to create a voltage offset at DC, right? So I have to spend extra power. Now, having said that, and you guys should do this calculations yourselves once, I promise you that the extra power you spend on doing this is way less than the power you would spend to just upsize this device. Okay? Because even though making the devices smaller makes their offset bigger, the amount of current you have to spend here in the first place is proportional to how big that load resistance was also in the first place. So if you make the devices smaller, the load resistance gets bigger. Even though you need a wider range in the DAC, the net power actually goes down. Or the net, let's say, DC power you'd have to spend will go down. But having said that, indeed, that is one of the negatives of this topology, which is you have extra DC power consumption. Okay, there's one other thing which is maybe not a negative per se, but we do have to be a little bit careful about. Yes?
Well, you've got the, like, one gets going to the sign thing in there, working on for that, so fuck that up again.
Oh, I see. Okay, so you said, that's actually a good observation. You said, look, I've got one bit that's kind of going to these sine thingies. I'm going to have some other bits that are going to this current DAC. And if I'm like dynamically moving those things around, then to quote you literally, I could F that up. Okay, and indeed you can F that up. Now, fortunately, remember, the whole point of doing this was to cancel a DC effect. So I think most of the effects that you're talking about, in terms of Fing that up, would be related to the timing of those two things could be different. And indeed, if you had this, if this was supposed to be a high speed kind of thing, that could indeed get messed up. But if it's really mostly a DC effect I'm after, I'm not super worried about that. But it is a very good point. There's something else that even from a DC standpoint is maybe not a negative, but is a limitation of this particular approach. So let me maybe ask you guys. Can I cancel as big of an offset as I want in this? In other words, let's say, can I cancel a 600 millivolt offset? Yeah. Okay, you said because you're canceling it at the output, it actually cuts into your swing, a lot like the sort of output offset cancellation we talked about before. That is true, but I think you're going to hit something even before that.
Well, I mean, I guess the problem is you've already gained up whatever your offset is, and so now you're going to cancel the gained up offset, so you're going to spend more current because your resistance to respond.
Okay, so you said that I've already gained up the offset. It is true I've already gained up the offset. Now, if you sort of think about it, the amount of current I have to spend in this thing is really proportional to this current. Right? Because basically that offset just goes through the GM of these input devices to become a differential current at the output. So if I want to cancel a certain amount of offset, I basically have to figure out what's the equivalent current to cancel that same voltage at the input. Now, that actually, all of the statements I just made actually embed a hint as to where this might be limited. So, when I say that this thing has a GM, is the GM really fixed? No. So in particular, if I was to draw a plot of the differential output current from that original input pair versus the differential input voltage, what would it look like? Oh, okay. You said hyperbolic tangent. To use our simple model that we had just, discussed in class, it would be kind of straight and then clip. And then on the other side, straight and clip. And just as a reminder, where does this happen? V star. All right, now you guys tell me. What's the problem? Why does this limit my offset cancellation range? How is it that we cancel the offset? What is it that we're doing? Okay, we're dumping a current into the output. All right, so let's just walk through that graphically. So let's say that from whatever reason, your offset was such that you were initially sitting there on the curve. Right? All All right, well, so if I was initially sitting there on the curve, that would mean I would have to take this amount of current and dump it into the output to cancel that effect, right? All right, so now you guys tell me, if my offset's out over here, what's going to happen?
That's how offset works. I would imagine that the zero cost.
No, that's correct, but remember, it's not that I'm actually adding things directly at the input. I'm first taking the input voltage, going through the GM, as Rachel said, and then adding a current to its output. Right? So in other words, in order to get back to the input, I have to go through the reverse of this transfer function. And because of that, indeed, if your offset is too big, or rather, to say it another way, the range of offset you can actually cancel here is basically limited by that V star. Because if the thing clips out, right, I'm just going to apply that much more current, and all it's going to do is just clip the input stage even further. Right? It's not really going to do anything. Okay? So with this topology, the main, let's say, limitation is that you can only cancel offsets roughly up to sort of the V star. Now, I've drawn things here a little bit, loosely, in that obviously there is still some slope on that curve there. It's just that obviously things get a lot gnarlier in terms of the step sizes you need in the current to get a certain voltage resolution out of it, right? Because if this really, it's hard for me to draw, but if it really just has a very, very small slope on it, that means that the steps in current you need to do obviously are much smaller to get the same voltage resolution on the other side. Right? Make sense to everybody? Or? Okay. So as I said, this does have some limitations associated with it, but this is kind of my own personal default solution because it does have a lot of nice characteristics associated with it. Having said that, there are some other, let's say, tricks that people have come up with that in particular try and address the issue of being forced to spend extra power just to cancel a DC offset. And so the basic idea as to how you might do that is actually to say, you know what? Let me build a circuit that will always use whatever DC current I have to actually give me some transconductance, but do it in a way that I can actually program the offset. So to see how you might do that, this is again, by the way, going to be sort of a preamp-based method, although you can implement it in other circuits as well. So I'm still going to use my load resistors here. The trick the idea looks something like the following. What I'm basically going to do is, instead of building my differential pair the normal way I do it, I'm instead going to sort of split it into smaller pieces. And in particular, I'm going to build sort of like two differential pairs, where, and by the way, this time around, I didn't just have a bad drawing. I intentionally sort of drew these transistors in a little bit of a weird way. What I'm going to intentionally do is in each of those differential pairs, I'm going to have one of the transistors be really big and the other one be really small. But I'm going to have two of these things. And just to be 100% clear, this is going to be VI plus, this is going to be VI plus, this is going to be VI minus, and this is going to be VI minus. Okay? So, if I make the bias current in these two diff pairs the same, then on the net, the whole thing is symmetric, right? Because I have a big device and a small device for VI plus. And for VI minus, I also have a big device and a small device. But now notice, if I take, for example, some of the bias current from here and feed it to there, now it's as if I have a bigger device on the VI minus side. Right? And in particular, if I took all of the bias current and fed it over here, now I have this weird looking circuit where I have a really big device on one side and a really small device on the other, which clearly would push my offset towards the VI minus side. Right? So again, the whole idea here is that simply by moving current between I1 and I2, I can basically sort of intentionally tune the level of asymmetry in my input devices, and by doing that, tune the offset, the relative input referred offset. But I can still do that in a way that allows me to actually always use that current to actually get a GM out of the structure. So just in case people are sort of interested, this was first proposed by a guy named Brian Casper, and I believe this was published in JSC, if I'm not mistaken, in around 2002 or 2003. I don't 100% remember, but if you do a search for it, I'm sure you'll find it. And this is sometimes referred to as sort of a Casper DAC. And it was actually used in exactly the same context you guys are interested in, meaning it was used as a way to cancel the offset of a comparator inside of a high-speed serial link. So as I said, the good thing about this is that indeed it allows you to always use the bias current, right? Because either which way, you've always sort of got that bias current giving you some kind of a GM. And by the way, just to make sure it's sort of absolutely clear, the way you generally use these things is you keep the total bias current fixed. You just move it from one side to the other. Okay, so if you wanted a more negative offset, you move it over here. You want a more positive offset, you move it over there. Now, having said all of that, again, advantages, I get to use the bias current, but there's a couple of disadvantages. So what are a couple of the disadvantages you guys might see from this? Okay, you said you're not sure about the linearity of the DAC. Turns out it's actually pretty darn good. Okay, because in some senses you can kind of think of it as you're just linearly interpolating between the individual offsets created by each of these two guys. You're right, it may, you have to sort of do a slightly more detailed analysis, but it actually turns out to be pretty darn good. What else is maybe not ideal about this? Okay, you said you'd have a big capacitance at the source of these transistors. That's absolutely correct. What does that mean? Like, what's bad about that? Yeah, so your high-frequency common mode rejection is probably not going to be great. That is true.
You can fix that by another current mirror, right?
Okay, you said you can fix that by another current mirror. That's actually a really interesting discussion. Let's come back to that in 1 second. Okay, because there's some subtleties with that one. But in principle, what you're saying is correct. But we'll come back to that one. What else? I'll give you a hint. It's related to common mode rejection. I'll give you another hint. In your guys' project where you have the PAM4 receiver and, I give you the mean condition for this particular example, and you actually have the full 5x larger swing going into your thing. Roughly speaking, how much offset, how much offset do you think you're going to need to inject into this thing? Just give me ballpark numbers based on your phase 2. Like, how big were your signal swings? Say that again? Tens of millivolts. And when you do the 5x larger than that, it becomes, let's say, 100 to a couple hundred millivolts, right? All right, well, if I need a couple hundred millivolts of offset, and we'll see why this is in 1 second, I will most likely need to steer the current almost fully to one side or to the other. What's bad about this circuit when you steer the current fully to one side or the other? Yeah, exactly. It's horribly asymmetric, right? So you guys thought I was joking, but if you recall, the first thing I showed you was something that looked like this. Well, guess what? I just did it, right? Because if I really needed a large offset range, I intentionally put this whole circuit in a way that basically had a really big inherent asymmetry in it. Okay, so issue number one with this particular thing is indeed the asymmetry when you have large V offsets. Okay, it turns out, by the way, that it's not only that you have asymmetry, it's actually even the sort of fundamental thermal and flicker noise of this thing will vary as you change those offsets. Okay, that's sort of an exercise I'll leave you to sort of do at home. But there is one more, let's say, perhaps not negative, but limitation in this thing. So what do you think sets how big of an offset you can actually create in this thing in the first place? Like, what sets the range? The bias current, is that what you said? The bias current RO. Well, notice in this particular thing, Right? It's not that I'm really, let's say, taking a bias current and dumping it into the resistance. I'm actually just deciding how much of the bias current flows through this differential pair versus through this differential pair. Okay. So you said the range is the ratio of the big width to the small width. And it's basically directly related to that. Now, we just have to be a little bit careful because remember, I'm interested in a voltage range. So what's the units? Yeah, okay, so what's the magic parameter that we've used since, like, I don't know, lecture 2 or 3 in this class that's probably what you're looking for? V star, there we go. Okay, so what really sets the range in terms of the offset cancellation is the difference in V star between this big device and this small device. Oh, absolutely. You said, is the V star changing as you move the currents around? Absolutely, but notice the limit is clear. Right, the limit is if I put all of the current on this side versus all of the current on that side. Right, that's kind of like the plus and minus. So if I push it all the way to the plus, my offset is basically the difference in V star between the big device and the small device. And indeed, the way you control that difference in V star is by how big you make this big device relative to that small device. But it does indeed say that if you want to get a big offset range, you basically need a big delta V star. Now, that has, by the way, another sort of subtle implication. So if you need a big delta V star, as an example, let's say you need 300 millivolts of delta V star. What's the smallest V star you can actually use on average? Okay, you said 150. It turns out it's even worse than that because, I would have to make one of the V stars 0, right? And the other one is 300. So really it ends up being that basically you can only effectively get away with a 300 millivolt V star. So the other thing that potentially is bad in this is that if you really need a large offset cancellation range, it may force you to use a higher V star than you otherwise wanted to use. Which means that again, even though I'm actually using the current always, the sort of relative current efficiency or power efficiency I'm getting is now again being limited by sort of this offset range rather than sort of fundamentally what I needed to actually drive the signals at a certain frequency. Is this clear to everybody? Or? So you asked a very good question, which was, are you trying to cancel the offset of this or the comparator that follows it? You guys tell me. What are you trying to do? Both.
Isn't the range not V star? It's like V star times GM times the gain of this?
GM times the gain of this. So I don't think the units of that quite work out because that's a current.
I mean, you're trying to cancel, like the comparator offset is a voltage offset.
Okay, great question. So you said, hey, wait a minute. The comparator offset is a voltage at the output of this thing. So you're absolutely correct that the comparator offset is basically attenuated from an input referred standpoint by the gain of this structure. Right, so if the gain of this structure is high, then really, in some senses, you're only canceling your own offset. Right, because the comparator offset relative to the input has a smaller effect. Having said that, for better or for worse, you're probably not going to be able to get very high gain out of this thing. Because again, remember we said that we wanted these load resistors to be small compared to the RO, which tends to push us to relatively low gain types of topologies. By the way, your guys' life this year at least is even worse than previous years because you guys are dealing with 4PAM. Right? And I told you that your signal swings vary by 5x. So you have to cover not only this thing's own offset and the comparator offset, you also have to cover the range of variation in the signal itself in order to be able to set the thresholds in the right spot. Okay, so again, understanding sort of how these things trade off with each other is pretty important because it could really drive which of these topologies you might happen to use to try and get the overall best, let's say, trade-off between offset range and power and asymmetry and etc. And by the way, for those of you who haven't actually read it, asymmetry will matter because I've thrown noise on all your power supplies now. So you'll see it if things are actually pretty asymmetric. It'll actually show up as noise at your output. Any other questions on this? Or?
In terms of project, do you expect us to build like a 7-bit adder and register file?
Oh, okay, great. Thank you for reminding me. So the question was, in the project, do I expect you guys to build, a 7-bit adder and a register file and all this other stuff? No. Okay, so what you need to do for the project is anything that's just some digital logic or something like that. I don't care. I assume that you know how to build that, or somebody else somewhere in the world knows how to build it and can give it to you. Okay, so you don't have to build any accumulators or this actual feedback loop or anything like that. All you really have to do, and let's be specific with the comparator as an example, all you really have to do is, of course, build the comparator itself, the DAC, meaning the thing that would actually physically affect your offsets, and any extra, let's say, switches or anything you need to sort of make the input actually go to 0 volts or to wherever your target offset actually is. Okay? So in other words, anything that might sort of sit or interact with your high-speed signal path, that you actually do have to build. But anything that's like, digital control logic or some other thing that's, off on the side somewhere that really doesn't matter, that you don't have to build. Is that clear? Or? Now, by the way, just in case you thought I was being nice, when you build, for example, these DACs, you better keep in mind that there's offsets in those transistors too. Okay, so when you build the DAC, you actually have to build a DAC that really will get the step size you claim you're getting. So again, user beware, because, there is some additional, let's say, sizing and algorithm, or let's say design procedure you'll have to apply to get the DACs to actually behave the way you want them to. And that's not, by the way, not just because I'm trying to be mean, it's to try and make sure you actually understand why this thing could happen, because otherwise if there's an offset, you just make all these things as small as you can, and you might get an unrealistic result. Any other questions on this? Or? Great. So if not, as I said, I'll be out on Thursday, so some of you will be watching this then. If anybody has questions or anything like that, feel free to send us email or post on Piazza, and I'll see you guys all